So in this chapter, I want to cover tool length compensation. You probably remember that if we did the tool change, so we could add a tool, but so far the tool length was not considered. So if you move to Z0, it with or without tool, our simulation behaved the same way. In reality, typically tool length compensation is active to compensate the length of the tool. So a couple of little bit theory about how this works on a different controller. On the Siemens controller, that's a little bit different than, for example, on FANUC. On Siemens, you can have the tool length is activated using a D command, and the D can have a number from 0 to I think up to 9. D0 means the length compensation is deactivated, so that's comparable to G43H0 on the FANUC controller. But the difference is the other numbers. In the Siemens case, the Siemens can have per tool up to 9 compensation settings, and the second tool will also have a D1 and D2. But D1 of tool 1 and D1 of tool 2 can contain different lengths. So the length and radius settings are a parameter of the tool, and not like on FANUC a global parameter. So on FANUC H10 can be used for tool 1 and tool 2. It just contains a length, and that will be used for the compensation. So that's really a little bit different. Typically on Siemens, if you activate the tool change, after tool change, typically the first length correction is active. So in most cases, at the end of the M6 subprogram, it makes sense to write D1 that activates the first length compensation of the tool. Multiple length corrections for one tool are only required if you have multi-step drills, for example, or of course on turning tools that could be relevant. On turning tools, of course, we are also not only talking about the length compensation, but you also need to compensate the tool in at least 2 directions, typically X and Z, but it could also be that you need to compensate in Y direction. So we are actually talking about 3 different lengths that can be compensated. Finally, the D setting on the Siemens controller, they contain all that. So associated with a D1 can be up to 3 lengths, the radius for the radius compensation, and for turning tools also the tool nose position, the quadrant, and even more. On the Heidenhain, there are 2 ways to use tools. One is to just use a tool call and then specify with the tool name. The Heidenhain can have a table that contains the length and radius, and exactly 1 length and 1 radius. The other option is that in the tool definition you have the length and radius values directly being specified. If I remember correctly, our out-of-the-box CCF file uses the first mechanism. So instead of taking the values specified in the ANSI program, we read out the length and radius values from the ONT. On FANUC, like I mentioned before, you have registers, and these H registers are independent of the tool. So if the H10 register contains a length of 100, you can use that for tool 1 and tool 20 if they are 10 millimeters long or 10 inch long. So that's really independent, and you activate it with G43. What also comes or gets relevant here are the working planes. So on a G17 that is typically active on a milling machine, the length of the tool gets compensated in Z direction, and should you have turning tools or probing tools, then X and Y are compensated in the other directions. On G18 the length gets compensated in Y direction, and on G19 on X direction, and the others change accordingly. Here also we can make use of this concept of the geo-axis that you probably remember we have very quickly covered in the channel configuration when we created our initial MCF file. I told you that the Siemens controller uses those geo-axes to define a coordinate system with X, Y, and Z direction. On turning machines it could be that the Y-axis is not existing, but anyway it defines a coordinate system, and the direction of this coordinate system that defines the working plane. So for example, if the geo-axes are X, Y, and Z, which is in 99% of all cases true, then G17 means the length will be compensated in Z direction, and X and Y are the plane that will be used, for example, for a circle, or that determines the plane that is used for radius compensation. And for G18 and G19 this is accordingly. So the geo-axis always contain X, Y, and Z, but there's a method in CSE that you can use, get first axis, get second geo-axis, and other methods get first axis, and depending on which plane is active they change the value. We will make use of that just shortly to that you better understand what's meant here. So to actually implement it, the first thing I will do after our tool change is to add a D1 and then try to see what happens. So after the tool change I will move to X, Y, Z 0, and after D1 I'm doing that again to see if our tool length compensation has any effect. So that will be my test program. If I execute that, of course the D1 will produce an error message that the code is not defined. So what I can do is to in my MCF file add an address, select D, click OK, sort it alphabetically, and then I need to customize that. So again, the D metacode contains a parameter, that is the value. So in my example the value will be 1 because I've programmed D1. So what I will have to do is, what I want to do actually, is I have defined a tool in my ONT with a given length, and the length of the tool specified by the parameters of the tool, I would like to use this length to compensate to do the length compensation. So I somehow need to get access to the length parameter of CAM. To do that there is a special command. So first of all, before that I would like to do an if command and check whether I'm activating my tool length compensation or not. So if 0 equals value, stop comparison needs to be 2 equal signs. So in this case I need a special behavior. We can define that later. Then let's look up the documentation, and there's a special section for where's the tool handling? Yeah, there's a set tool correction command, and that basically tells CSE which tool correction should be used. In this case that's a tracking point index, and for typical milling tools that's of course always 1. So I will use set tool correction. That tells CSE which tool length compensation I want to get for which tracking point. Then this can be used by CSE to query the application and to look into the ONT for the current tool that is currently active on the spindle. Give me the length correction values, and then we can use those. So the first command I need to activate is set tool correction. Elements as after. Parameter, first one is the tracking point index, so this would be value. The second one is the name of the carrier that holds the tool, in this case in our machine that is S. And finally I have two options. If I have no active tool, so in case I did not do a tool change and I still program a D1, what kind of behavior would the controller have in this case? Would he issue an error message, or will he just ignore the D1 and basically behave like no tool compensation is active? And that can be specified by this optional error message. I will just omit that. So the next thing I need to do is to actually compensate the length, and that is done through a concept called transformations, and there's a whole section about transformations that can be activated, reset. Where is this place? Displays origin, makes an actual offset, and then with another activate transformation you can actually activate the transformation. So we will use this concept for the tool length compensation. So first of all I need a command name, and that will be activate transformation. A transformation you can think of like a matrix, a 4x4 matrix that contains offsets in all three directions. And of course for the tool length compensation we mainly want to compensate in Z direction, so we will just use the set offset of this matrix. In CSE, to be able to change the matrix stored in the transformation, you need to first deactivate the transformation, and that's done with not very smart with activate transformation, and then the parameter false to deactivate it. The second parameter, or actually the first parameter of activate transformation, is the name of the transformation, and for the tool length compensation we can use one of the built-in transformations, and that is called $tool. We will make use of the same concept for zero offsets and local offsets later on, where we'll create our own transformations, but for the tool length compensation in most cases you can use the built-in transformation. Then, like I said, you need to deactivate it first, so this parameter active is of type Boolean, so to deactivate it, it needs to contain false. And finally there's a parameter that tells whether this is modally active or just for the current line. In this case it doesn't matter, so I can write false here. The next thing we should do is just duplicate the section to reset the transformation. So in case it contained any offset in any direction before, I want to clear that, and that can be done using the reset transformation that just contains the name. So we can do that. In the end, we need to activate our transformation again. So that will be done with true. And in this case, since the tool length compensation is modally active, so it's active until you change it or you do a tool change, the second or the third parameter here needs to be true to make it modally active. And now the main part is still missing. We need to do the actual offset, and that is done by displays origin with 4 parameters. So we displays origin The name of the transformation is $tool. Then you can specify whether it should be an incremental offset or an absolute offset. Since we've just cleared it and the transformation is empty, that doesn't matter, it's the same thing. But to be sure, I'm using the absolute value. Then we need to specify in which direction we want to compensate, and that is typically Z. We want to compensate in Z direction. And finally the offset value, and that is now the length of the tool. And to get the length of the tool, we have a couple of methods in the tool handling section. That is called get L correction, get Q correction, and get Z correction. If you remember this presentation. Where is it? Yeah, here it is. So if G17 is active, then get L correction will contain the correction in Z direction. For turning machines or for certain other types of tools, you will also have to use get Q and get Z correction to get the other values. But for typical milling machines, get L correction is completely sufficient. So for the value we will type get L correction. Get L correction doesn't have any parameters, so that's why I can just leave empty brackets. And that will displace in a given direction, in this case in Z direction. Let's see if this is all we need. Actually, what we can do is here this if condition is still not correct. In any case, if I want to deactivate my tool compensation, so if I program D0, I still need to do the reset transformation to clear the current values. So what I can do here is to move this down here, and in the then branch I can put the set tool correction and the displace origin, and then activate the transformation. So to explain that, what I just did, in any case, whatever happens independent of which value of D is being programmed, I deactivate my transformation so that I can change it, then I'm resetting it so that it contains no offsets, and I activate it again. So if I program D0, oh, that's actually not equal now. If I program D0, then I will just clear my transformation and no tool length compensation will be active. If D is not equal to 0, so in most cases it will be 1, in this case this condition should be true, and I will use set tool correction to get the tool length compensation from the ONT into CSE, and then use displace origin to actually compensate. And let's try if this works. So I will save it, save my MCF file. I just did the test program already, and then we can reset and try it. So first of all, without tool length compensation, I'm moving to X, Y, Z 0. That still doesn't do anything. I'm still at the same position. Then I'm activating my tool length compensation. So far nothing happens, but if I move to the same position now, then still nothing happens. Why? Why is that? Okay, so this looks correct, so there must be something else wrong. Let's look in the NC program again. Okay, it can't work. We have G91, which is incremental active, so these are not absolute movements, these are incremental movements, and of course that doesn't work. So we need to change that and write G90, then it should work. So let's test it again, simulate the file. So we are in 0, 0, 0. Now activate our tool length compensation, and then move again, and in this case you will now see that we get a compensation and move up depending on the tool length. So that seems to work now. So the next thing we can do is to make this more general. If you remember, in the channel configuration we've added the access to the channel, and then CSE automatically filled out this GEO access section. Well, actually machine configurator filled that out. And by default we use access with the name X, Y and Z and assume that those are the GEO access. If this is not correct, you can change that. So like I said before, this configures the coordinate system that the machine will use, and it basically defines can be used for the working plane, for the tool radius compensation, also for the direction of the tool length compensation, and defines the orientation of the matrix stored in the transformations. So we defined the GEO axis, but we did not make use of that. And if you look at the controller in the documentation, we will find under transformations that there are methods to get the first GEO axis, second GEO axis and third GEO axis. So in our machine, get third GEO axis will always return the Z axis. And then there are commands like set working plane, or get first axis and get second axis, and depending on the work plane setting, get first axis or get third axis. In G17 this will return Z, in G18 it will return Y, and in G19 it will return X. So that really depends on the current working plane. And we can also start to implement that and make our D meta code more flexible. So we can open that, and instead of compensating hard-coded in Z direction, we can here write get third axis, and then depending on G17, 18 we compensate in the right direction. We save that, and what we can also do is to add a meta code for G17. Customize it, and execute a command. Like we've just seen, the command is set working plane, and the parameter is XY. We can look that up. Set working plane, and the parameter is XY for the X plane. For the XY plane. You can of course replicate that and create G18 and G19 accordingly. So if we save that and execute our program again, we should see that it still works. But in this case more general, and if you program something else than G17, which is the default, we would compensate in a different direction. We can actually test it. So copy that into G code, G18. G18 would be XZ. Oh, I should add it to the program somewhere. G18. Invalid arguments. Oh, it's different order. Should always look it up. So it's not XZ, it's ZX. So in this case, we should now compensate in Y direction. And now the machine moved 75 tool length in Y direction. Of course, with this tool and G18 doesn't make any sense, but that would be the behavior of the real machine. Okay, so that's how tool length compensation works.